Okay, so if you have a graphing calculator in hand and you are trying to solve a very challenging equation, some graphing calculators do have a solver, and that's a possibility to be able to use that. Not all of them have a solver. However, all of the graphing calculators can solve a very complex equation using the method I'm about to show you. Even if you have a graphing calculator that has a solver, you should pay attention to the method that I'm about to show you, because on the AP exam, the people who write the AP exam, they understand how the solver works and they know how they can tie it up into knots, and they do that sometimes. But if you use the method I'm about to show you, it avoids that situation. Okay, so let's say you have some sort of complex equation, and I'm just talking general terms here at first. And let's say we have something like, something here on the left equals something here on the right. And so what you want to do is you want to get 0 on one side, one side or the other, whatever side makes it easier. So let's say we have, let's say we move the triangle over, so minus the triangle equals 0. So you get 0 on one side, and the stuff that you have here on this side. Now, you can clean it up some. You don't want to waste a bunch of time doing a bunch of algebra, but clean it up enough so that you can actually plug it into your graphing calculator, and you're going to put it into the y equals, so that you can graph it. Now, what you're going to do is you're going to graph the function, and then you're going to find where y is equal to 0. Let's see, that would be x-intercepts, wouldn't it? Okay, so this is how we're going to do it. That's the general procedure. You let the calculator, you graph it, you solve for the x-intercepts, and you let the calculator do the heavy lifting. Okay, I'm going to show you a couple of examples just real quickly. So let's say we had a max-min problem and optimization. And let's say we had the curve y equals the square root of x plus 4. And I want the shortest distance from the point 3, -1 to the curve. Okay, so a sketch could be helpful at least. Okay, so y equals square root of x plus 4. Vertex, it's half parabola, vertex there at -4, 0. And it's opening up and to the right, and there's a basic sketch of that half parabola. Okay, 3, -1, right there, and we want the shortest distance to some point that's on the xy. So now this is x comma y. Now distance formula, so distance equals, you got the big square root. You can do x minus 3 or 3 minus x. I'm telling you it's better if you do the variable minus the number. So x minus 3 quantity squared plus, and then y minus a -1, so y plus 1 quantity squared. Now, you guys know when you're doing optimization and you need to do the derivative, you need to get this side over here all in one variable. You do not want to be doing the derivative with optimization with two variables over there, even though we know how to be able to do that sort of thing at this point now. But with optimization, one variable. So I need to substitute for either x or y. Well, we happen to know that y is root x plus 4. So if I substitute that Where I see the y's, we can get d equals square root x minus 3 quantity squared plus, okay, in place of the y, I've got root x plus 4 plus 1 quantity squared. Okay, so we have the distance, what we're trying to minimize, in terms of one variable. So, we do the derivative. So d prime. Now, when you do a square root, isn't it always 1/2 times the quantity to the negative 1/2? So that's really 1 over 2 times the root times the derivative of the guts. And the derivative of the guts, you got x minus 3 quantity squared, so that's 2 times x minus 3 to the first times the derivative of those guts, which is 1, plus, and then you got the derivative of this part right here, so you got 2 times root x plus 4 plus 1 to the first times the derivative of those guts. And you got another square root in there, and so you've got 1 over 2 times the square root of x plus 4 times the derivative of those guts, which is just 1. Okay, yes, I should probably go ahead and fill this in right here. That was x minus 3 quantity squared plus root x plus 4 plus 1 quantity squared. Okay, now I've taken the derivative. This is a very complex equation, obviously. Now, what do? Don't we set it equal to 0? And obviously you could clean up here, but we're setting it equal to 0. It's an equation. Wouldn't I multiply both sides of the equation by this denominator right here to clear that out? Yes, do that. But we want to minimize the amount of algebra that we're going to do. But if I multiply both sides of the equation by 2 times this big mess of a square root and multiply both sides of the equation by it, that part reduces out. And I'm left with 2 times x minus 3 plus 2 times root x plus 4 plus 1 times 1 over 2 root x plus 4 equals 0. Now, again, we don't want to waste a bunch of time with cleaning up algebra, but are you prepared to plug this into your calculator right now? If you're prepared to plug this into your calculator right now, you could plug that into your calculator right now. Now, let me just show you one more thing here. The 2 right there and the 2 right there reduce. Okay, so we have 2 times x minus 3. Yes, if you could go ahead and say 2x minus 6. Plus, we've got root x plus 4 plus 1 all over root x plus 4 equals 0. Now, you could keep on doing a bunch of algebra cleanup, but at some point you're going to want to stop wasting time with the algebra cleanup. This is not too bad to plug in the graphing calculator right here. So if I plug this in the graphing calculator right there, y sub 1 equals, so grab my graphing calculator. And so 2 times x minus 3 quantity, 2 parentheses x minus 3, plus, okay, now if you have a fraction, make sure it knows what's in the numerator and what's in the denominator. And it won't know what's in the numerator or what's in the denominator unless you use parentheses. So I'm going to show parentheses around the numerator. And so parentheses, root x plus 4 plus 1, close the numerator, divided by root x plus 4. Now, some of your graphing calculators, they use open parenthesis, close parenthesis, and so you got to be a little bit more careful with all that kind of stuff. But anyway, make sure that you get it to a point where you know you can plug it in your graphing calculator accurately. Okay, so now we're solving for the critical point. Okay, and just based off of our sketch right here, isn't the x value going to be something positive and fairly small? So probably just do zoom decimal. Zoom decimal. Sometimes you have to manipulate your window a little bit. Zoom decimal, and we're looking for where y equals 0. And where y equals 0 is where it's crossing the x-axis. So use your calculator's capabilities to solve for that x-intercept. So second calc, the 0 function, you need a left boundary, you need a right boundary, and let the calculator do the heavy lifting. And I don't know if you can see that right there, but it says that x is approximately 2.300808. So 3 decimal place accuracy, and this isn't my final answer, so I maybe should go ahead and actually be a little bit more accurate. So x is approximately 2.3008 point, or excuse me, not point, but 08. Okay, now it always helps to actually answer the question. If I was asking for the shortest distance, make sure you give me the shortest distance. This is my critical point. If I was trying to justify it, I'd do d prime, and here's 2.300808. That's where it's equal to 0, and I'm trying to show a minimum, so it should be going from negative to positive. By the way, look at my derivative. It's going from negative to positive. Okay, anyway, so if I wanted the distance, now take this value and we're going to plug it into where I have the distance with just the x's. Okay, so I'm going to clear out of there, and I'm going to 2.3000808. I don't feel like plugging that in a bunch of times, so I'm going to store it, stow alpha A, and enter. And so now anytime I do the alpha A, it represents the 2.3000808. Okay, so my distance, square root x minus 3 quantity squared plus the square root of x plus 4 plus 1 quantity squared. Now I could do the stuff on the inside here first and then do the square root, and that's fine, or you could do it all at once. So square root, I'm just going to do it all at once. Open parenthesis, alpha A minus 3 squared plus, open parenthesis, square root, alpha A plus 4, okay, get out of the square root, plus 1, close the parenthesis, squared, okay, and it's all entered in there right now. And so if I press enter, my minimum distance is approximately 3.579. Minimum distance is approximately 3.579. Okay, now it always answer the question. If they want the minimum distance, give them the minimum distance. I mean, it comes from the critical point anyway. If they want the ordered pair that gives you the minimum distance, then give them the ordered pair. Answer the question. It's always a good idea to answer the question. Okay, so the second problem, I wanted to go over a mean value theorem problem. Somebody was asking me about this earlier in the day today. So f of x equals 2 sine x, that was the function, and the closed interval was negative pi over 2 to 5 pi over 2. Okay, so first off, does the mean value theorem apply? Well, is the function continuous on that closed interval? Well, sure. The function is continuous for all reals. You guys need to know that. It's also a smooth curve for all reals, and so therefore it is differentiable on that open interval as well. So the mean value theorem applies. So since the mean value theorem applies, I need the derivative. So f prime of x is 2 cosine x, and we also need f of b minus f of a over b minus a. Okay, so f of b, so I'm doing sine of 5 pi over 2, sine of 5 pi over 2, that's 1, times 2 is 2, minus, now f of a, okay, sine of negative pi over 2. Sine of negative pi over 2 is negative 1, times 2 is negative 2, all over b minus a, so 5 pi over 2 minus a negative pi over 2. Okay, so we get 4 over 6 pi over 2. In other words, 4 over 1 times 2 over 6 pi, which is 4 over 3 pi. Okay, so we're going to set that equal to the derivative. Now, if you want, you could go ahead and replace the x with a c. You don't have to. You can just, we're going to find all c that are in that open interval. Okay, so we've got 2 cosine x equals 4 over 3 pi. And so you look and you go, oh, I should go ahead and divide by 2 or multiply by 1/2. So cosine x, if I multiply by 1/2, I get 2 over 3 pi. And at this point, you're going, well, I don't really recognize that. I mean, that's not 2 over 3 pi for cosine. That's not something we recognize. But if we have graphing calculator in hand, it's not a problem. Okay, so what do? We get 0 on one side. So let's bring the 2 over 3 pi to the left. So cosine x minus 2 over 3 pi equals 0. Okay, and so now we are going to graph this in y sub 1. And then we're going to solve for the where y equals 0 in this interval, negative pi over 2 to 5 pi over 2. Okay, so now, again, there's a fraction here. It only knows what's in the numerator or the denominator if you tell it what's in the numerator or the denominator. So you need parentheses around the 3 pi. So let's grab the calculator, and I'm going to clear out what was in there, and y equals, clear that out. So I'm going to be doing cosine x. Make sure you're in radians when you're doing trig stuff, or anything really with calculus. Make sure you're in radians. Cosine x minus 2 divided by 3 pi. And I have parentheses around the 3 pi because otherwise it won't realize it's in the denominator. Okay, now the other thing here too, remember that when we're doing the mean value theorem, you're only looking for c that's in the open interval here from negative pi over 2 to 5 pi over 2. And there might be some outside of that. We don't want to get distracted by it. So window, I'm going to do my x minimum is negative pi over 2. So negative pi divided by 2, and press enter, and it'll convert it to a decimal. And then the x maximum is 5 pi over 2, so 5 pi over 2. Okay, and I was on Zoom Decimal, so the y min and y max are probably okay. That's probably fine. Okay, so let's go ahead and graph this. Okay, now as we graph it, remember we're looking for where y equals 0, and I gave it the boundaries. So every time it's touching or crossing the x-axis in that viewing window, those are all solutions. And I don't know how well you can see this, but it's crossing the x-axis here close to the edge on the left, and then right here, and right here, and then again it crosses right over here very close to the edge. There's actually 4 solutions here. You let the calculator do the heavy lifting for you, and you solve for those x-intercepts, and those are the C's. So for example, I'll do one of them there with you. So second calc, the 0, and get to the left-hand side of it. Press enter, get to the right-hand side of it, press enter. Okay, so one of them is approximately negative 1.357, 3 decimal place accuracy. So one of the C's, C sub 1, is approximately negative 1.357. And then you go through and you find the other 3. And so second calc, find the x-intercept. And the second one's approximately positive 1.357. Three decimal place accuracy. Move on. Get the next one. .926 approximately. And finally, the last one that's in that open interval from negative pi over 2 to 5 pi over 2. .640. Yes, you need the 0 because you need to be 3 decimal place accurate. And if you don't put the 0 there, then it could be a 0, a 1, a 2, a 3, or 4. So that's how you quickly let the graphing calculator solve an equation that otherwise you would have difficulty solving.